In this video, we're going to review exponential functions. So we begin with the definition. So an exponential function with base a, and there's some conditions on a, so a has to be positive and in fact not equal to 1. Okay, so if you have such an exponential function looks like f of x is a to the power x. Okay, so notice here the variable is in the exponent. So this is different than for polynomials, where the variable is the base and then the exponent is a number. Here, the base is a number and the variable is the exponent. Now, I just want to point out why we need to remove a equals 1. Okay, then f of x is going to be 1 to the power x, and 1 to any power is just 1. So this is a constant function. Right? It's just a horizontal line, so it has different properties. So it won't match all the other properties of exponential functions, so that's why we want to remove that special case. Exponential functions are useful and they arise in many real-world problems. So for instance, when a population grows, or you might have noticed recently the spread of the COVID-19 is sort of exponential. It follows an exponential pattern. So we are going to begin with let's think about the graphs here. So we're going to do two graphs on this grid. Okay, so f of x is 2 to the x and g of x is 2 to the minus x. So we want to compare these. So because we don't really maybe know what these look like, we're going to do a table of values. Okay, so we'll do 2 to the x first. So let's say I do x equals 0. Okay, then this is going to be 2 to the 0, which is a 1. Okay, so we get a point at 0, 1. If I do x equals 1, then I have 2 to the 1, which is 2. So I get a point at 1, 2. If I do x equals 2, it's 2 squared, which is 4. Okay, so I get a point at 4. X equals 3. Okay, that's 2 cubed, which is 8. So you can see it's starting to grow really fast. Okay, what if I use negative numbers, so like negative 1? 2 to the negative 1 is actually 1/2, right? It's 1 over 2 to the positive 1. So I'm going to be at 1/2 here. If I do negative 2, it's 2 to the negative 2, which is 1 over 2 squared, or 1 over 4. So I'm even closer to y equals 0. Okay, and negative 3 is going to be similar. 2 to the minus 3 is going to be 1 over 8. So I'm even closer to 0. So my graph is going to look like this. So then it starts growing really quickly. But as we get really negative, it has a horizontal asymptote at y equals 0. Okay, now let's switch colors here. What if I wanted to do 2 to the negative x? So when I put in 0, I get 2 to the minus 0. Okay, that's still 1. So I still get a point at 0, 1. When I'm at 1, now it's 2 to the minus 1, which we already said was 1/2. Okay, when I'm 2, it's 2 to the minus 2, which we know is 1/4. Okay, 2 to the 3. So when I do 3, it's going to be negative 3 in the exponent, so that's going to be 1 over 8. Okay, so you can see that our horizontal asymptote here is now this way. When I do negative 1, it's 2 to the negative negative 1, so that's 2 to the 1, so I get a point at negative 1, 2. When x is negative 2, it's 2 to the negative negative 2, so it's 2 squared, or 4. Okay, and you can probably guess negative 3 is going to be at 8. So this graph looks the same, but flipped over the y-axis. Okay, now 2 to the negative x is actually 1 over 2 to the x, to the positive x. And you could write this as 1 to the x over 2 to the x. So you could actually think about this as 1/2 to the power x. Okay, so this one is g of x. And the first one we did here is f of x. So this is actually the general shape. So f of x, this is the general shape when a is bigger than 1. And over here, we have the general shape for a between 0 and 1. Okay, so it's like having a negative exponent. Okay, so that's sort of what the graph looks like, depending on your value of a. Okay, so some properties that we can see from the graph. The domain, there was no bad x values, so the domain is negative infinity to infinity, or you might want to say all real numbers. Okay, the range for both was y bigger than 0, or an interval notation from 0 to infinity, right? We can never get a negative number because it's a number to some power, okay, and our number is positive. Now, the limit as we go to infinity, this depends on your choice of a. Okay, so if a is bigger than 1, then as x gets really big, we're following the purple line. So our y values are also getting really big. Okay, so this is going to be infinity if a is bigger than 1. But if a is between 0 and 1, then we actually approach 0 as x gets really big. So that's going to be following the blue curve. Okay, so the y values are getting close to 0. If we go to negative infinity, this just flips. So we get 0 if a is bigger than 1, and infinity if a is between 0 and 1. So when we're solving equations with exponential functions, you're probably not going to be surprised that the exponent rules are going to be important. Okay, that's why we spent so much time reviewing those at the beginning of the term. So let's say I want to solve for x in these equations here. So it says 2 to the 3x equals 2 to the 7. Okay, now notice that these both sides of this equation, they're using the same base. Okay, so when they have the same base, it means that the exponents need to be equal if the numbers are going to be equal, right? So like on this side, we have 3x 2's all times together, and on this side, we have 7 2's all times together. So if I get the same number, there has to be the same number of 2's on each side. So that means that 3x needs to be equal to 7, which means that x is actually 7 over 3. So that's going to be the solution to that equation. What if they're not the same base? So here we have 2 to the 2x plus 1 is equal to 8 to the x. Okay, so we don't have the same base, but we actually know that 8 is base 2. It's 2 to the 3. So we can actually rewrite this equation using base 2. So it's 2 to the 2x plus 1 is equal to 2 cubed to the power x. Okay, when you have a power to a power, you multiply the exponents. So this is 2 to the 2x plus 1 should equal 2 to the 3x. Now we have the same base, so we know that the exponent should be equal. Okay, so now I'm just going to subtract 2x on both sides. And that's going to give me that 1 is equal to x. Okay, so here I need x equals 1 in order for that equation to be satisfied. Let's try another one. So here I have 1 over 9 to the power 2x is equal to 3 to the power 4x minus 1. So not in the same base, okay, but I see this 9 here, and I know 9 is 3 squared, so maybe I can put them in the same base. So 1 over 9 is actually 9 to the negative 1. Okay, so that means that this is actually 9 to the negative 2x equals 3 to the 4x minus 1. And we know that 9 is 3 squared. Okay, so it's, now I have 3 squared all to the power negative 2. So I multiply those powers. So it's 3 to the negative 4x equals 3 to the 4x minus 1. And now I have the same base, so the exponents need to be equal. Okay, so if I subtract 4x on this side, or on both sides, I guess, then I'm going to have negative 8x is equal to negative 1. So dividing by negative 8, I get x is 1 over 8. So that's going to be the solution here. So, so far we need, the only way we know how to solve these exponential equations is to be able to write them in the same base. Okay, if we cannot write them in the same base, then we need another technique, but that's going to come later after we talk about logarithms. Okay, so we're actually going to need a logarithmic function to solve those. Okay, there's one base that is special. Okay, it's particularly useful, even in real-world scenarios. Okay, it's called E, or Eulers Constant, and it's just a number like pi. So it's an irrational number, 2.71828818, and it keeps going. Okay, it's an infinite non-repeating decimal. Okay, so this is Eulers constant, and it's just an irrational number. So we cannot write it as a fraction. It's an infinite non-repeating decimal. And it actually comes from a limit. Okay, so E is actually the limit as m goes to infinity of 1 plus 1 over m to the power m. Okay, that actually is E. Okay, so that's where it comes from. But it's just a number that's between 2 and 3. Okay, so you just want to remember, okay, E is not a variable, even though it's a letter. Okay, it's not a variable, it's just a constant. Okay, so it's special, but it behaves in the same way. Okay, so let me just give you an example here. So if this function, oops, let me just make this a bit better here. Okay, so if this function is 2 to the x, okay, and this function, I'm trying to exaggerate this a bit, but if this function is 3 to the x, then e to the x just lives in the middle of these two. Okay, because it's between 2 and 3, so when we take powers of it, they're going to fall between the powers of 2 and 3. Okay, so it has all the same properties as every other exponential function. It's just a number. So it's an allowable base because it's bigger than 0 and not 1. So that's a special base that we use quite often. You'll see when we start taking derivatives why this one is particularly useful or convenient for us. So let's just do an example. So suppose salmonella bacteria found on chickens grow rapidly in a nice warm place. Okay, the number present in some potato salad T hours after you take it out of the fridge is determined by this equation. Okay, f of t is 500 times 2 to the 3t. How many bacteria are present after 1 hour? Okay, well that's going to be f of 1, right? Because it was the number of bacteria t hours after it's taken out. So after 1 hour, I just want to plug in t equals 1. Okay, so if I do that, I'm going to be 500 times 2 to the 3 times 1. So that's 500 times 8, which is actually 4,000 bacteria. Now, how many were present when we removed it from the fridge? So that's after 0 hours, so no time has passed. How many were currently in it? So it's going to be 500, 2 to the 3 times 0. So that's 2 to the 0, which is just 1. Okay, so it started off with 500, and after 1 hour it had 4,000. How many hours will it take for there to be 32,000 bacteria? Okay, so here we want t so that f of t is equal to 32,000. So that means that we want 500, 2 to the 3t to equal 32,000. So before I can solve this, I want to get the exponential function by itself. So what I'm going to do is divide both sides by 500. Okay, so that I have 2 to the 3t by itself on this side. And over here I just have 64. Okay, now 64 is in fact a power of 2. It's 2 to the 6. So that means that now I have the same base, so I need 3t to equal 6. Okay, so then if I divide by 3, this is 2. T equals 2. Okay, so what that means is after 2 hours, there will be 32,000 bacteria. Okay, how do I know how fast the bacteria double? Okay, so here I want to know when did they double first. Okay, so I want f of t so that it's 2 times our original amount of bacteria. So that's 2 times 500. So I want to know when was it equal to 1,000. Okay, so that means I want 1,000 is equal to 500, 2 to the 3t. So I divide by 500. So that's actually 2 is equal to 2 to the 3t, so 2 to the 1. So I need 1 is equal to 3t, which means that t is 1/3. Okay, now this is 1/3 of an hour. Okay, 1/3 of an hour is actually 20 minutes. Okay, so took bacteria 20 minutes to double their number. So that's just some examples using exponential functions, their graphs, some properties about them. Later we're going to talk about the logarithmic functions and how they relate to the exponential functions, and then we'll be able to solve even more different types of exponential functions.